So far, we have introduced topological spaces and continuous maps between them. So, two topological spaces are the same if they are homomorphic. So, it is natural to ask, to classify topological spaces up to homomorphism. So, for instance, all these examples that we have seen so far, we can ask if they are homomorphic to each other, or maybe one of them is homomorphic to a product of others, etc., etc. So, one way to show that two topological spaces are not homomorphic is to find some topological property satisfied by one but not the other. So in this lecture, we will introduce one such topological property. So we shall understand the notion of being connected. So intuitively, if we consider, let's say, the interval something like this, the union of these two intervals with the subspace topology, then this should not be connected. Whereas the interval 0, 1 should be connected. So I'm trying to suggest that the word connected should correspond to something which is intuitive. And it does correspond to something. So let us see the definition, the abstract definition of being connected. Let X be a topological space. So suppose there are non-empty and disjoint open sets U and V such that X is equal to U is the disjoint union of both these, then we say that X is disconnected. So to say that X is disconnected, we need two non-empty disjoint open subsets whose union is all of X. And we shall say that X is connected if it is not disconnected. So now that we have defined the notion of connectedness, we can ask several questions. So we can ask the following questions. So the first one is the real line connected? The real line with the standard topology. And what about Rn? So if R is not connected, so what are the connected subspaces of R? Okay, if X and Y are connected, then what can we say about the product? Is the product connected? Then we saw several examples of topological spaces, in fact of topological groups. So we can ask if those are connected, etc., etc. So this is unitary groups, orthogonal groups, unitary groups, special orthogonal groups, special unitary groups, and so on. So let us begin by so let us begin by attempting to answer the first few. So proposition. So this is like the proposition which we will need. Let U containing X be dense if U is connected. Then X is connected. So the proof. So we'll prove this by contradiction. So we assume that X is disconnected and arrive at a contradiction. So as X is disconnected, so this means that we can find a disconnection. So that is, there are non-empty, disjoint, open sets U and V such that, okay, so let's say U1 and U2, because we've already used this notation U. So we have disjoint sets U1 and U2. X is equal to U1 disjoint union U2. So we simply intersect this with U. This with U to get U is equal to U intersection U1 disjoint union U intersection U2. So as U is dense, this implies U intersection U1 is non-empty and U intersection U2 is non-empty. So this implies that U is disconnected, which is a contradiction. So this proves the proposition. So as a simple corollary, we get let A containing X be a subspace. So it's a subset and it has a subspace topology. So if A is connected, then a closure is connected. And the proof is obvious. A is dense in a closure. There's something which we had seen. So apply the previous proposition. To this inclusion. Okay. So next let us show that the interval 0, 1 is connected. So proof. So let us assume that we will prove this by contradiction is disconnected. So then so there are non-empty disjoint open sets U and V such that 0, 1 is a disjoint union of U and V. So without loss of generality, we may assume that 0 belongs to U. So let us consider the set S. This consists of those x in 0, 1 such that the interval 0, x is completely contained inside U. So clearly, zero is in S. So we let A be the supremum of those x and x, of all x and x. And now we claim that A belongs to U. So by the definition of supremum, there is a sequence of ANs converging to A, where ANs belong to S. So in particular, this implies that ANs belong to U. So, but as the complement of U is open, so this implies U is also closed. So we have a sequence of ANs which is in U and it is converging to A, and since U is closed, so this implies A belongs to U. So this proves our claim. So in particular, this implies the interval 0, comma A is contained in U. Now as A is open, as U is open, so this implies there is some positive epsilon such that a minus epsilon, a plus epsilon is contained inside u. Okay, so before that, so let us assume that so we are making the second claim now. We claim that a is equal to 1. So if not, then a is strictly less than 1, and we can, and as a is open, I'm sorry, as u is open, we can find epsilon positive, which is very small, such that this set a minus epsilon, a plus epsilon, this intersected with 0 1 is contained inside u. But then this implies that the interval 0 comma a plus epsilon is contained inside u. But this implies 0 comma a plus epsilon by 2, let's say, is contained inside u. So this contradicts a being the supremum of S, as a plus epsilon by 2 also belongs to S. So this implies that a is equal to 1. So this implies that the whole interval 0 1 is contained in U. This implies V is empty, which is a contradiction. So this proves the proposition. So one of the observations very simple observation we used in this remark was, we used in this proof was, X is disconnected if and only if it contains a non-empty open subset U, which is also closed. Sometimes such sets are called Clopen sets. And the second observation we want to make is, this is also equally obvious, if X and Y are homomorphic, then X is connected if and only if Y is connected. So as a corollary of this second remark, we see that as 0 1 is homomorphic, the closed interval 0 1 to a comma b, so where a strictly less than b are in R. So it follows that these finite intervals are connected. So let us use this, the fact that we have proved that these finite intervals are connected, to show that R is connected. This is also easily seen. So proof. If not, then R is equal to U disjoint union V, where U comma V are non-empty, open. So we choose A in U and B in V, and assume without loss of generality A is strictly less than B. So then when we intersect with the interval A comma B, we get that A comma B is written like this, which implies A comma B is disconnected, which gives a contradiction. So this completes the proof. So we have shown that R is connected. And as another corollary, so let Y be a non-empty connected subspace of R, then Y is one of the following. So A comma B are real numbers. So proof. So the idea of the proof is very simple. So we let A be equal to infimum Y for Y and Y, and B be the supremum. So then A is less than or equal to B. So if A is equal to B, so then this implies that Y is a singleton set A. So let's consider the other case. So if A is strictly less than B, then we claim every C such that C lies between A and B then we claim that this interval A comma B, open interval, is contained in Y. So if not, there is C in this interval such that C does not belong to Y. And so we can write Y equal to Y intersected minus infinity comma C, disjoint union Y intersected C comma infinity. So which implies that Y is not connected. So this gives a contradiction. So which implies that, as we claimed, A comma B is contained in Y. And clearly we have Y is contained in C. So the rest of the proof is left as an exercise. Okay. So the preceding corollary gives us a nice description of the connected subsets of R. And next, we want to show that Rn is connected. Okay, so there's an easy way to see this, which is left as an exercise. So the idea is, given any 2 points, join them using a line. So use this and the connectedness of 0, 1 to show that Rn is connected. But we can also prove a more general theorem which says the following. So let x and y be connected topological spaces, then their product is connected. So proof. So if not, there are non-empty, disjoint open sets A and B contained in x cross y such that x cross y is A disjoint union B. So now recall that in lecture 8 we saw that when we look at x naught, we fix x naught, and when we look at x naught cross y contained inside x cross y with the subspace topology, this is homeomorphic to y. In fact, the natural map y gets mapped to x naught comma y is the homeomorphism. So we will use this. So intersecting, so we intersect x cross the disconnection with x cross y, we get x naught cross y, which is homeomorphic to y, is equal to x naught cross y intersected with A disjoint union x naught cross y intersected with B. So as y, which is isomorphic to x naught cross y, is connected, so this implies that this x naught cross y is completely contained in A or in B. Because otherwise we will get that x naught cross y is disconnected, but that same is saying y is disconnected. That's not true. So similarly, we have x cross y naught is completely contained in A or B. So now we pick any point. X naught comma y naught in A. So this implies, so by this preceding line, that x cross y naught is contained in A, which means that x comma y naught belongs to A for all x in X. So this implies that x cross y is completely contained inside A for all x in X. But this implies that x cross y is contained in A, which is a contradiction. So as a corollary of this very general thing, this theorem, we get that Rn is connected. and proposition. So this proposition states that image of a connected set is connected. Topological space under a continuous map is connected. Maybe I should put this as a remark. So let f from x to y be a continuous map. So assume x is connected, then f of x with the subspace topology so let me just emphasize. Yeah, there's only one topology we can give. I mean, one natural choice topology from y is connected. So proof. If not, then f of x is disconnected. So that means there are open sets u and v in y such that when we look at their intersection and these two sets are non-empty, they are disjoint, and f of x is their union. But now this will imply that x is equal to f inverse u, disjoint union f inverse v, and as f is continuous, so this implies that f inverse u and f inverse v are open. So this implies that x is disconnected, which is a contradiction. So we will end this lecture here.